welcome to lecture 56. So, we have been discussing about the general theory of orbit perturbation. So, we will continue with that, but today before we start working with the evaluation of the Lagrange bracket. So, before that we will review the concepts we have been discussing in the previous few lectures. So, what we have done that orbit this movement of a body heavenly body about another heavenly body in the relative terms, we have written it like this mu by r cube r, and this also we have written in terms of minus del u. Now, the solution to this problem mu by r cube r equal to 0. So, because this consists of 3 vector second order or 3 scalar, this is a vector equation. So, 3 scalar second order differential equation. So, total 6 constants are involved in this. And already we have identified those constants A, E, then I, small omega and capital omega. The another constant, see, will make little difference here, that if we are given x, y, z and x dot, y dot, z dot at any instant of time, say at t 0, which we indicate here by putting the subscript 0. So, corresponding orbital parameters, it is a, e, I, small omega, capital omega and theta 0, whatever the theta value at. This is the corresponding orbital parameters, but here in this case once we are telling that there are 6 constants involved. So, the last constant will identify with what we write as sigma, okay, where from where it is appearing. So, if you look into the Euler equation, we have this Kepler's equation we have written. So, we solved this equation, and while integrating, so we got it in the form m equal to n t minus t equal to E minus E sin E, where E is the eccentric anomaly, this is the mean anomaly, and the quantity here n t minus this quantity we can write as n t plus sigma, where sigma equal to minus n t, and t is called the time of Pereggi passage. So, rather than taking this theta as because see the once you convert it into the orbital parameters. So, you can see that the theta is varying with time. Okay. If you take it for a particular instant, then it is okay, but if you take it for as a general variable, so theta is varying with time. Okay. You are taking not as a particular instant of time, but in a general manner you are writing. So, theta will keep varying with time. So, this will not appear as a constant. So, rather than taking that sigma, which is written as sigma equal to minus n t. So, this is taken as a constant. So, either minus n t or either t. So, either of them can be chosen as the constant of integration. Okay. Sometimes instead of t or minus n t, also it is usual to use m at a particular instant of time, which is the mean anomaly at a particular instant of time. So, now if we look back and the equation we derived for the conic section E cos, say this was something like phi minus beta, which we wrote as L 1 plus E cos theta, where theta we have written as the true anomaly, this is x, y, z, the inertial frame, and then we have the orbit here. This point was n prime, and perigee position is lying somewhere here. Okay, so, this angle we have written as omega. So, what appears here in this place? So, actually what we have written here theta. So, it is a we are getting theta as phi minus beta. So, phi is being measured from certain reference. So, say the phi, if we measure from this reference, if we measure phi here in this direction, okay, let us say this is phi, okay, and then beta will become this angle from here to here. So, here in this case whatever the beta is appearing, it is nothing but your small omega, which is the argument of perigee, argument of perigee. But the argument of perigee we have derived in some other way, but the fact is that the beta appearing here, it was nothing but the argument of perigee. It is being referred to certain reference line. So, phi is being referred to the line n prime O n, okay, and then beta is to this place. So, therefore, this angle is your theta, which is shown here in this place. Okay. So, as a whole here how many parameters were involved in this A and E involved. In the L, both L A and E are involved, here also E is there, another parameter beta. So, in this equation itself you have 3 parameters involved, which are A, E and small omega, but we wrote it in a way that it was not visible. Okay. Now, it becomes more purposeful to discuss all these things. So, here of course, we have derived omega in some other way, which we got in the terms of x, y, z, x dot, y dot, z dot, etcetera. So, x, y, z, and then we had also this capital omega, and in terms of I we have got it. Now, the time of perigee passes means at this point, this how much time it is taken to this place, this we write as t. Sometimes it is also written as, instead of writing this is also written as tau. Okay. So, either of them can be used. So, time of perigee passes, and from there then if the time taken to let me use another color, time taken to this place, this we write as t. Okay. So, you can see that from here to here, then this time is t minus capital T. So, t minus capital T, this is directly related to your mean anomaly by this equation. So, what we have been discussing here, that instead of using theta, because this is not appearing as a constant, rather it is varying with time. So, we use this sigma equal to minus n t as the constant of the orbit. Okay. And these 6 constants, they are nothing but the constant of integration in this equation, or either here in this equation. So, this term so this part is important here, considering this sigma, because once we are considering the orbit perturbation. So, immediately we can see that in the case of the orbit perturbation, if this is the osculating orbit and the true orbit is going like this. So, if the disturbance is not present, your satellite may be here, but if disturbance is present, your satellite may be located here in this place, or either say your satellite is here and we move it little bit from this place. So, this is the delta r perturbation produced because of your the term we have written r double dot equal to minus del u plus r. So, this was the perturbation potential. So, because of this is the perturbation produced in the orbit, otherwise it would have followed the osculating orbit, which in this case it becomes a Keplerian orbit if the disturbance is not present. Okay. So, if the disturbance is present, so this node also this will rotate. Okay. Here in this case you can see that what we have written here, the this time of perigee passage we have indicated by here t, this position, this t will also change. Okay. Omega and t, they are not the same thing. Remember, omega and t, they are not the same thing. This is the time taken from this place to this place, from the reference to this place, which we are calling as the time of perigee passage. And this is the, here this part is the angle omega. So, this angle, and if you multiply this t by the mean anomaly, which is we are writing as n. So, this does not give you this omega. Okay. So, we have to be careful about this, because the angular velocity is changing over only over a whole one period of time. So, from where in the Keplerian orbit, from wherever it is starting, it will get back to the same place. Now, once the theta is varying, so whatever the angle here indicated, this omega angle, it will not be covered in the same time. If you multiply it with the mean anomaly, then what I mean that if you multiply mean angular rate with the time of perigee passage, you are not going to get this. Otherwise, there is no meaning to writing this A E I small omega and t or either sigma, what we are using here, and capital omega. See, if both are the same, so there is no meaning to writing that these are the two different constants. Okay. So, this part you should remember, and perhaps I have not discussed this till now, but this is the right time to get into this, and I have described this. This is exactly what the things are taking place. So, this t will also vary if the perturbation term this r is present. Okay. Now, we can start with the evaluation of the Lagrange bracket, what I have written here. So, earlier as I have told you that we will divide it into the total all the elements A, E, I, small omega, capital omega and sigma. Instead of minus n t, we are writing this as the sigma. Okay. So, this can be divided into three parts, and we can write it as A is sigma and I small omega and capital omega. So, these two groups we divide it, and this also we have discussed earlier, this I will indicate by alpha r and this by beta s. So, number of the Lagrange brackets already we have discussed that out of total 36, because this forms a Lagrange bracket element, they form 6 into 6 matrix. So, out of that the diagonal one is 0, and thereafter here we have total of 9, in this place we get total of 3, in this place we get total of 3, and here just with a opposite sign. Okay. Here also on this side, as we have discussed, we will get 3. So, on the left side of the diagonal, here it will be a minus of this. Similarly, here in this place, whatever the sign it comes with, on this side this will be negative. or otherwise. So, if then we divided it into two parts. So, one part, this part will refer to from here to here, this part is corresponding to A E sigma, and this part is corresponding to I small omega and capital omega. So, you can see that Lagrange bracket, then it can be written as A, which of course is 0 according to the property of the Lagrange bracket we have written. Similarly, A E. So, these are just referring to your alpha r and alpha s, or alpha r alpha s, okay, where alpha r varies over 1 2 3 and s also is 1 2 3. While the mixture one, this one where I have shown this 9. So, that corresponds to terms like A I etcetera. Okay. So, you can see here immediately, if I write here A E sigma and here I small omega capital omega, A E sigma I small omega capital omega. So, here corresponding elements are like this. In this place, similarly for related to this, you will get A I, then A omega and then A sigma. The terms will appear like this. So, total of 3 plus 3 and plus here we are getting total in this place 3 into 3 9. So, 9 plus 3 12 plus 3 total 15. Because of the skew symmetry here, the another thing that you should notice that here the matrix formed by this skew symmetric matrix, okay, this is non singular. Okay. So, this matrix formed by Lagrange bracket C I comma C j, this is non singular. Non singular means its a determinant is not 0, although this is skew symmetric. This is because this is of even order. Even order. Okay. So, even order skew symmetric matrix, skew symmetric matrix, it is a non singular, while odd order skew symmetric matrix will be singular. That means, if I have a 3 into 3 skew symmetric matrix, so this is bound to be singular. Means if this is matrix A and it is a skew symmetric, so determinant of this will be 0. So, we have to evaluate, our purpose is to evaluate the Lagrange bracket. So, using the first two properties, that is like the A, this bracket will be 0, okay, and also A t or A sigma, this will be equal to minus T A. So, this was a second property, okay, we have already written this, okay. And the third property that we have written, it was dou y dou t C I comma C j, this equal to 0. That means, the Lagrange bracket of the if we are taking the time derivative of the Lagrange bracket. So, this quantity is going to be 0 and this we have proved earlier. So, let me just rewrite those data statement. So, this we have written as is just Lagrange bracket is just dependent on the osculating elements and not on its derivatives, which are constant. So, if we use this property that the oscillating this Lagrange bracket it is independent of this time. So, therefore, we can utilize it to find the evaluate the Lagrange bracket, say what I mean here in this place, that if this quantity is independent of time. So, that means it is a derivative, either you that means this Lagrange bracket you either evaluate at this point or either at this point or this point of the osculating orbit, it is going to be the same, because it is independent of time, it is not depending on time. Okay. That means, I can also evaluate at the this perigee location, and this property we are going to use next to evaluate the Lagrange bracket corresponding to here alpha r alpha s. Okay, so, with this we have so, this is our osculating ellipse, and we draw the axis here. This is xi and eta, this is the focus, and this is our auxiliary circle. If this point, this is r, so and this angle is theta. So, xi we can write as r cos theta and eta as r sin theta, the x and y component in the plane of the orbit, and from here the orbit will get perturbed. Okay. And already the various relations we have derived in the case of the while we were discussing the this Kepler's equation. So, at that time we have derived all the relations. So, I am not going to again write it here, and simply I will write the result. This is A times cos E minus E, and this is A times 1 minus E a square times sin E. So, with these two basic equations, and in the Lagrange vector while we are looking for. So, there we have to the alpha r, alpha s, this we have to evaluate, and there what we have looked into, that this will be dou iota by dou xi by dou alpha r and dou xi by dou alpha s, dou alpha r, and so, we need to evaluate these Lagrange brackets. This is the Lagrange bracket, and we have expanded it. So, we need to evaluate these determinants or the Jacobian. Okay. Now, for evaluating each of them and where we are going to use, we are going to use this in finding out the quantities like A e, A t, etc. And also we have m equal to n times t minus t, which can be also written as n t plus sigma, as we have written earlier. So, this is our third equation, and n equal to mu by a cube under root or n square equal to mu by a cube. So, these are some of the information we can use to solve this problem. So, dou by dou t C j C k or C I C j, whatever the term we have used. Okay. So, this quantity we have written perhaps in terms of C j and C k. So, we will continue with writing this. This quantity is going to 0, and what does this mean? This implies that C j C k is constant for all values of t, and hence can be evaluated at any point in the oscillating orbit. Therefore, for convenience, we opt to evaluate the bracket, Lagrange bracket, at the perigee. So, for this evaluation, we about the perigee point, we consider an infinitesimal value of E. So, for an infinitesimal value of E, we consider this. So, what does this mean? That say here we want to evaluate at perigee. So, we just take a nearby location which is infinitesimally close to this and expand our equation which are given there. So, E minus E sin E, this equal to m, and so if we expand it, this can be simply written as E minus E sin E equal to m, equal to n t minus t, and therefore, from this place E can be written as t minus t divided by 1 minus E. Okay, this is the whole process. Okay, we are trying to evaluate at this point. So, we take a nearby point, expand it. So, basically we have linearized it and then try to evaluate the Lagrange bracket at this point. Now, so the cos E we can write as 1 minus sin square E cos square E equal to, and this becomes then 1 minus E square. This is approximately, because sin E for a small value of E, this will be equal to E, and therefore, cos E will be equal to 1 minus E square to the power 1 by 2, which we can approximately write as 1 minus 1 by 2 E square using binomial expansion. Okay. So, if we utilize this information in our work, so this the equation for the xi we have written. So, that becomes A times cos E minus E. So, the cos E is then 1 minus 1 by 2 E a square minus E, which we can write as so. I will work one or two Lagrange bracket, all of them it is not possible to do here in this lecture, because it is a every one is very time taking, and obviously I am not going to derive all the equations. For that I will give you some supplementary material which can be used for looking into those derivations. I will, after covering the basics, I will be writing the results, and the derivation of those results you will find in the supplementary material provided. Okay. Similarly, the eta then becomes, this is equal to, this is r cos theta, r sin theta, this equal to a times 1 minus E a square times sin E we have written. So, sin E equal to E. So, this becomes A E minus 1 minus E a square. So, eta then can be written as E, already we have written, E we have written here somewhere, in this place. So, you will use this equation to and insert here in this place. So, eta becomes then eta we can write as, this was n t minus t divided by 1 minus E. A times 1 minus E times 1 plus E and t minus t divided by okay. Similarly, this xi, this can also be written in terms of n and t. This will become a 1 minus E and minus 1 by 2 n square t minus t square divided by 1 minus E square. And now, we are ready to derive this eta dot and xi dot. So, first we work the xi dot term. Xi dot will be a times, if we differentiate this. So, this quantity we are going to get this as, now n square term is there. So, n square already we have written as mu by a cube. So, once we differentiate, so this gives us a is there and then minus n square divided by 2 times 2 t minus t divided by 1 minus E square. So, minus a n square a, 2 cancels out, t minus t divided by 1 minus E square. Similarly, the eta dot we can write as n a times 1 plus E by 1 minus E. Okay, so, this way we have got these terms. Now, we need to evaluate the terms appearing in the Lagrange bracket. So, there we have the first determinant by dou xi by, let us say that we are looking for alpha r alpha s. So, alpha r we replace by A and alpha s we replace by E. Okay. And then what will be the value of this Lagrange bracket? This is what we are looking for. That means, we have written alpha r equal to A and alpha s equal to E. So, we need to replace this alpha r by A and alpha s by E. So, here then the derivative becomes dou xi by dou A, dou xi by dou E, and then dou xi dot by dou A and dou xi dot by dou E. This we need to evaluate, and the other bracket. So, this quantity dou eta by dou A, dou eta by dou E, dou xi dot by dou A and dou xi dot by sorry, this is eta dot by dou E. This is the quantity we have to find out. So, each of them then we need to evaluate. So, dou xi by dou A, now xi equation already we have written. So, directly from there A is appearing. So, immediately we can see this can be written as 1 by 2 n square t minus t whole square divided by 1 minus E square. This is the first term, the A was appearing here in this place, this place. So, this we have differentiated. Next, n is also a function of A. So, therefore, we need to differentiate that too. Okay. So, the next term will be A times 0 plus 1 by 2 3 n square t minus t whole square and divided by A times 1 minus E square. That means, this is dou by dou A, mu we can take it outside, A to the power minus 3, and this will turn out to be mu times A to the minus 3 mu times A to the power minus 4 and this is nothing but then you can write as minus 3 n square divided by A, because mu by A q is n square. So, this is the thing we have used here in this place, and this can be reduced finally to 1 minus E minus n square t minus t whole square divided by 1 minus C square 1 minus E whole square, and then plus 3 n square divided by 2 t minus t whole square and 1 minus E square. So, this minus sign which was appearing here, that got plus, and A is appearing here. So, this A will cancel out. So, this is what we get, and if we try to evaluate at the perigee, that means we are evaluating at the point where t equal to capital T. So, at that point we get this as 1 minus E. This quantity will be 0, this quantity will be 0. So, we will get this as 1 minus E. Okay. So, basically this term we write as dou xi by dou A to be evaluated at t equal to 1 minus. Okay. So, this way we have to evaluate all the terms. Okay. Similarly, we have dou xi dot by dou A, this equal to 2 mu as we have written here, dou xi dot is here. So, once we differentiate this quantity, xi dot A is there and n square is also present. So, differentiating this, let me copy it here in this place, n square minus n square A okay. Maybe this time is over, otherwise lecture will get longer. So, we will continue this in the next lecture. Thank you very much.